Okay, it is time for the Chapter 6 review. After all the moving around and everything, I was beginning to wonder if y'all aren't going to see this until after spring break. But provided nothing else happens, you'll see it before spring break. Now, if you're watching this in future semesters, it may certainly be before spring break because you may be in the fall. But as of when I'm recording this now, it's the spring semester. We just made it through Snowmageddon 2021. And yeah, I'm ready to get back to work. So I'm recording this video. Okay, so I should have already shared my screen with you. On the screen, I'm probably up there in the top corner. Oh, wrong corner. It'll be up there in that corner, up there, right up there. I'm probably sitting right there. But for the most part, you should see the review. Okay, so for this chapter, we did our first of our two probability chapters. Chapter 6 and Chapter 7 both deal with probability. We just made it through the first chapter. So let's go through this review. Vocabulary, vocabulary is vocabulary. I did just find the typo here, so let me fix that. Sample space, event, simple event. Make sure you know what all those words mean. I'll probably use them throughout the review today, so if you don't know them, maybe you want to pause it and go make some flashcards. Because you will need to know it. Okay, let's look at number 1. A standard 6-sided die is rolled. What's the probability of rolling an even number or a number divisible by 3? So this has two events on it. The first event that could occur is we get an even number. Okay, so we're rolling a standard 6-sided die. That means our possible rolls could be a 1, 2, 3, all the way to 6. Now, an even number. What are our even numbers? 2, 4, and 6. Those are the 4 even numbers, or sorry, the 3 even numbers that we could roll. I can't count today, evidently. Okay, or a number divisible by 3. Well, let's see, what's divisible by 3? We've got a 3 or a 6. Those are our two options for this second event. So we've got two events here. Now let's put them together. What do I want to get one or the other. So I could get a 2, I'd be happy. I could get a 3, I'd be happy. I could get a 4, I'd be happy, and I could get a 6. Well, what's the probability I get one of those numbers? The probability of a 2, 3, 4, or 6 would be 4 out of 6, which reduces to 2/3. Now I could go all into this, oh, well, let's do the addition rule and all this. No, just keep it simple. We're rolling a die, even number, 2, 4, 6. Divisible by 3, 3, 6. Okay, well, what all numbers could I get? 2, 3, 4, and 6. Hey, that's 4 of our options. 4 out of 6 reduces to 2/3. A is the answer. Now, if you notice on the other reviews, I've tried to type a lot in there. This one really doesn't lend much typing. It's more of a math. This chapter is very math heavy. After you've done the chapter, you'll probably agree there's a lot of math, a lot of equations. It would take too much time for me to type everything. So this one's going to be more of a handwritten review versus a typed review, but that's okay. Number 2, suppose a fair coin is tossed and a 6-sided number cube is rolled. A 6-sided die is rolled. What's the probability the coin lands on tails and the outcome on the number cube is less than 3? Well, let's look at these here. So what's happening? A fair coin is tossed, and we want the probability the coin lands on tails. So event A, actually this is one of those that maybe I could type it. This one we've got to deal with events. We just have to. There's no other way around it. We need to deal with events here. So let's get this all kind of set up. Shape fill, no fill, shape outline, no outline. Okay, so let's see here. Event A is going to be the coin, a fair coin, lands on tails. Event B, a 6-sided die. That's all a number cube is a 6-sided die. 6-sided fair die. Is rolled. Is rolled, and the result is less than 3. Okay. So there's 2 things that happened here. First, we flip a coin and it lands tails. Second, we roll a die and the result is less than 3. Those are our 2 happenings, if you will. So let's think about this. What is the probability of A? Well, a fair coin lands on tails, so that's going to be 1/2. If I think about B here, that means I roll a die and I roll a 1 or a 2. What's the probability of rolling a 1 or a 2? Well, that would be 2 out of 6. Which is the same as 1/3. Now, another thing to note here is that these are independent events. Events A and B are independent. So when we find the overall probability, then we just have to multiply. That's it. Just multiply. I mean, it doesn't matter what I flip when I go to roll the die. It's saying a fair coin is tossed, a die is rolled. End of story. Flip a coin, roll a die. Those are independent of each other. It's not like the die is like, you landed on the heads. I'm going to land on, no, they're independent. So the multiplication rule and independence says that the probability of A and B occurring for independent events is the probability of A times the probability of B. So that'd be 1/2 times 1/3, which is 1/6. There's our answer. That means answer choice A is our answer. Okay, so there's number 2. Number 3, consider the sample space containing all of the possible outcomes of rolling 2 dice. And that's here. I don't know what this red line is. I wish it would go away, but there it is. Let E represent the event that the sum of the 2 faces is less than or equal to 6. Okay, so I'm going to highlight that. E represents the event that the sum of the 2 faces shown is less than or equal to 6. What's the probability of E? Well, how many outcomes do we have total here? Let's look at that first. So total, we have 36 outcomes. Now, I need it to be less than or equal to 6. So I'm going to highlight ones in pink that satisfy my case. 1 plus 1 is 2. Those 2 go. Those go. Now we're up to 5. And now we go up to 6. And if I try the next diagonal, I'm up to 7. I've gone too far. You done messed up now, Aaron. Okay, so how many did I just highlight? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I can come over here and say the probability of E is 15 out of 36. And then I'll stop and look. Is this an answer choice? Yes, it is. It's actually answer choice E. Now, if it wasn't, we would probably have to reduce this, and you could. You could say this is 5 over 12. And then look and see, is it an answer choice? So notice they didn't reduce it on this one, so we have to adjust with them. Number 4, the following contingency table classifies the members of a certain government into political parties, liberal or conservative, and whether they support or oppose the spending bill that's currently up for adoption. What fraction of the liberals support the bill? So what fraction of the liberals support the bill? Well, here's our liberals right here. What portion of them support the bill? So that means I'm going to be looking at this value. But don't just tell me 47 out of 107. That's not what it's asking. This is like saying, what's the probability they support given that they're liberal? So remember, our formula for conditional probability says we need to do the probability that they support and they're liberal divided by the probability of liberal. The intersection is that 47 we circled. The number that are liberal, we can just say is the 58. So then we say 47 out of 58. If we needed to do a decimal, we could. But once you get an initial answer on the multiple choice, I would say, okay, time out, time. Let's look at the answer choices. 47 out of 58 is a choice. So circle it and move on. Remember, not necessarily on this test, but on the AP test, you have 90 minutes to do 40 questions. You can't be spending a bunch of time going all the way through. Work it, check your answers. Work it, check your answers. Okay, number 5. At Beth and Mary's Ice Cream Emporium, customers may choose 2 sprinkled toppings on their ice cream. The toppings are classified as either candy or fruit. Consider the chance experiment where the choice of toppings, candy or fruit, is recorded for each of the next 2 customers. List all the events in the sample space. Well, now this one's a little iffy. They're saying they can choose 2 toppings. We're going to say that if they choose candy, they're getting 2 candies. If they choose fruit, they're getting 2 fruits. So one customer is either going to get candy or fruit. That's what we're going to go with. That's my story, and I'm sticking to it. Okay, so let's note what each stands for. So we're going to let C equal candy. And then we're going to let, come back here, F equal fruit. Now, let's think about what could happen. We know C is candy, F is fruit. Got it. Okay, so the first customer could choose candy, then fruit. Or, well, back up. We got the first customer choose candy, second customer choose fruit. First customer choose candy, second customer choose candy. Now we've done all those options. So then we could say fruit, 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 candy. Those are our options. See how there's only 2, so I repeat it twice to fit the 2 options in there. Okay, now let's type up our answer over here. Let's put our answer in official answer form. Okay, so bracket. Remember, sample space, we need to include brackets. So we said, I'm going to go with candy, candy first. Candy, fruit. Fruit, candy. Fruit, fruit. So C, C, CF, FC, FF. There we go. Make it bold. And we're doing our answers in Blue. Okay. 1, 2, 3. There we go. So there's our answers. Candy. C is candy. F is fruit. So we could have candy, 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 fruit candy, or fruit, fruit. That's all there is to that one. We're just listing all the options. B, using our sample space in part A, list the outcomes for each of the following events. A is the event that both customers pick candy. Well, let's see. If I go up here for A, both customers pick candy, what would that event be? CC, right? Candy, candy. That's all there is to that one. B, the event that both customers pick the same type. Well, we could have candy, candy, or we could have fruit, fruit. They got to pick the same type. That's all there is to that one. C, the event that at least one customer picks a candy topping. At least one. That means at least one of them has to be candy. So we go through and we see, okay, well, let's see, candy, candy. Oh, there's one. Candy, fruit, fruit, candy. At least one of them was candy. I mean, I don't really know how else to explain that one. That one is just, it's you use your sample space from A to name the events, list the outcomes. I mean, that's it. Okay, C, display the sample space in the form of a tree diagram. Okay, so we have to put these 4 outcomes from A up here in the form of a tree. Well, let's draw it out. So my first customer, he's going to come in. What options does he have? He can get candy or he can get fruit. Now, regardless of whether he gets candy, the second customer comes in. What are his options? Candy or fruit? Again, second customer comes in. What are his options? Candy or fruit? And then you can even say, you can even go forth and say, okay, this represents candy, candy. This branch represents candy, then fruit. This branch represents fruit, then candy. This branch represents fruit, and then fruit. And notice we captured all 4 of our sample space options. And that's it. You just start at the beginning and work your way through. Now, as easy as this sounds, I have a feeling this is an important one, so it could appear on the test. You need to understand how sample spaces are developed. Okay, so that's all there is to number 5. Numero 6. An Australian snake, the diamond python, is about 3 feet long as an adult. In the study, the habitats of these creatures, microtransmitters, were in a study of these habitats of these creatures, microtransmitters were attached to their bodies and their locations were monitored. The following table displays the locations of these snakes by season of the year and habitat. The other category includes trees, logs, rocks, open ground, and under filtering covers or shrubs. So what we're really interested here is, did they go into a building? Which, no rope in my building? Nope. Or did they go into their natural habitats? Hopefully their natural habitats. I don't want a nope rope in my building, especially a python. Suppose these habitat locations are representative of dominant python behavior in the different seasons. Calculate the probabilities that, and then we have three different things to calculate. So A says a randomly selected diamondback would be located in a building. So in a building given that it's spring. Okay, well, let's see. Probability of building given spring. So I'm going to call this, let me write what we're going to call each of these. That way it's clear. So building, other, spring, I'm going to use SP, summer is SU, autumn, winter. Okay, so building given spring. If I do conditional probability, I have to do the probability that they're in a building and it's spring, divided by the probability that it's spring. Now remember, I'm saying probability, the counts work just fine. So we could say, oh, it's the number. Don't worry about that. Probability in spring divided by probability of building in spring divided by the probability of spring. Well, let's see here. Building and spring. It's going to be 10. So 10 goes on top. Probability of spring, 353. So 10 out of 353, which to 4 decimal places is approximately 0.0283. And that would be our final answer. Notice I didn't just give an answer. I didn't say, bleh, here's my answer. I showed the steps that I took. That's what you need to do. Show the steps you took. Because if you've watched the sampling Frappy questions, you'll realize that they look at your small details. When you give an answer, they look at your small details. Did they, okay, they got probability of spring. Okay, they got the denominator right, but they messed up the numerator. So it's partially right. They were partially on the right track. They just pulled the wrong number. So they'd give you partial. They would say it's partially correct. Maybe not essentially correct, but partially correct. That's better than being just completely wrong. It's wrong, it's done. So make sure you show your work. Can't stress that enough. I don't want you to just give me some random answer. How do I know you didn't just pull that out of your, where and say, here it is. Where'd you get it? So I need to wash my hands before I look at your number. Okay, B, a randomly selected diamondback would be located other than in a building, given that it's spring. So other than a building given it's spring or summer. This one's getting a little more complex. So probability of other given spring or summer. So this is going to be the probability of other and spring or summer. Divided by the probability of spring or summer. Okay, so let's look here. Probability of other and spring or summer. So other in spring, other in summer. It's going to be 343 plus 273 divided by probability of spring or summer altogether, 353, 309. So the top, 343 plus 273. That's going to give me, let's see, 6, 11, 616. Let me double check that calculation. Pretty sure that's right. 343 plus 273. Yep, 616 divided by 662. Which is approximately to 4 decimal places, 0.9305. There we go. So like I said to begin, this one's going to be this chapter is a lot of math. It's really math heavy. Okay, so C, found the probability that a selected diamondback is observed in a building or in the summer. So we want the probability of building or summer. Now this one, we're going to have to use our addition rule here. We're going to have to use the addition rule. We're going to have to say the probability of the building plus the probability of summer. But we've got to subtract out the probability that both happen because we don't want to double count. So let's do that. Building, how many were found in a building? So let me erase our markings here. We're interested in building, summer, and then we're in their intersection also. So 63 plus 309. Because that's building or summer, minus 36. Divided by how many total snakes do I have? 997. Why am I dividing by the total? Because I would have, if I didn't do it this way, I would have to do these individually. Probability of building, 63 over 997. Plus the probability of summer, 309 over 997. So I'm just doing it to where we just have to calculate the top and then divide it by the bottom. So this would get us 336 over 997, which is approximately equal to 0.3370 to 4 decimal places. So here we had to use the addition rule. So using the addition rule. Here, it'd technically be correct if we said using conditional probability. Except I can't spell probability. I mean, that's what we used. Again, up here we used conditional probability. So we should, technically, we should be putting that. Okay, number 7. Let's look at it. First though, I need a drink. Okay, number 7. I'm not going to read all that problem. They give us data. You can read it. I'm just not going to read it for the purposes of the video. Okay, now I will explain the table. So the table across the top, these are voters who are registered as Democrat, Republican, or Independent. This is who they voted for: Napolitano, Solomon, however you want to say it, and Mahoney. Now, Napolitano is a Democrat, Solomon is a Republican, Mahoney is an Independent. I don't want to use those letters for those names. I'm going to use N, S, and M. Okay, let's see what they ask. We're going to have to find all kinds of probabilities. What's the probability that a randomly chosen voter voted for Napolitano? So the probability for Napolitano is equal to, well, it's going to be the number that voted for, 282, over the total, 600. Probability of Napolitano is 282 over 600. Which equals, let's see, is that an even number? It is. So 0.47. That's really all there is to that one. B, what's the probability that a randomly chosen voter, so, is a registered Democrat? So we want the might help if I write in pen here. We want the probability of a Democrat. Well, there's 216 Democrats out of 600. So 216 out of 600. Going to be 0.36. C. What's the probability that a randomly chosen voter cast a vote for Napolitano given that the selected voter is a Democrat? Okay, so this is going to be conditional probability. So using conditional probability, we want the probability that they voted for Napolitano given they're a Democrat. That's going to be the probability of Napolitano and Democrat over the probability of Democrat. Well, let's see. What's the probability of Napolitano and Democrat? It's going to be 184 over the probability of Democrat, 216. So 184 divided by 216, that's going to be approximately, to 4 decimal places, 0.8519. Indeed. Commenting on this election, a local reporter said Napolitano won because she attracted a larger share of crossover voters. And then they say a crossover is a voter defined as one who votes differently than his or her party affiliation. So that would be like a Republican voting for a Democrat, an independent voting for a Republican. They don't match up. So in our case, a crossover, what's the probability that a randomly chosen voter cast a vote for Napolitano given that he or she is a crossover? Okay, well, let's look at crossovers. The crossovers are going to be the ones that are on the off diagonal. So Democrat voting for a Republican, Democrat voting for an independent, Republican voting for a Democrat, Republican voting for an independent, independent voting for either Democrat or Republican. Those are your crossovers. So I'm going to make a note up here that the highlighted ones are crossovers. Highlighted numbers are crossovers. Needed for Part D. Okay. So let's see. We want the probability of Napolitano given crossover. So what does this look like? This is the probability of Napolitano and being a crossover over the probability of being a crossover. Okay, so what crossovers, what highlighted ones voted for Napolitano? What numbers? 42 and 56. That's what's going to go on top. 42 plus 56. The bottom's going to be all of the crossovers. So 42 plus 56 plus 26 plus 45 plus 6 plus 5. Let me just kind of rewrite this a little bit neater. Okay, so let's see. 42 plus 56 is 98. On top. On bottom, let's add them all up. So 42 plus 56 plus 26 plus 45 plus 6 plus 5. 180. So to 4 decimal places, 98 divided by 180, that's going to be 0.5444. That's a probability that a randomly chosen voter cast a vote for Napolitano, given that there are crossover. Notice we kind of learned something in this problem. This would be kind of more leaning towards this synthesis type of question, where you learned something. If you didn't know what a crossover voter was before, maybe you do now. And we had to kind of stretch what we knew to apply it to this situation. But it wasn't something that was just totally unsolvable. Okay, so now let's look at number 8. Okay, so it's kind of funny that we're doing this one now because we're right in the middle of Girl Scout cookie season. And if you're a Girl Scout, you probably know statistics teachers seriously love Girl Scout cookies. The number of boxes of Girl Scout cookies statistics teachers order, like all important decisions, is determined by the roll of a 4-sided fair die, not a 6-sided. A 4-sided die. If a 1 appears, then we order 6 boxes. If any other number appears, we only order 2 boxes. What's the probability that a teacher places an order for 2 boxes of Girl Scout cookies? Okay. So let's think about this here. We want the probability that we order 2 boxes. Well, what happens up here? So if I roll a 1, then I order 6 boxes. If I roll anything else, so that means I roll a, excuse me, that means I roll a 2, 3, or 4, I order 2 boxes. Wah, wah, wah. Okay, it's asking on part A the probability that I only get 2 boxes. So that's the same as saying the probability that I roll a 2, 3, or 4. Well, what's the probability I get 1 of those? 3 out of 4, which is 0.75. That's all there was to that one. Okay. B, what's the probability that with 2 independently chosen statistics teachers, 2 independently chosen statistics teachers will each order 6 boxes? So let's come down here and let's define some events. So A is the event that teacher, or I'm going to just say teacher number 1 orders 6 boxes. B is the event that teacher number 2 orders 6 boxes. Those are the 2 events we're going up against. Okay, let me put these in our text color here. Okay, so now let's think about this. What's the probability that the first teacher orders 6 boxes? Well, I have to roll a 1. And the probability of that happening, so I'm going to just say the probability of A would be 1/6. Probability of B, sorry, not 1/6, 1/4. This is a 4-sided die. So 1/4. Probability of B is also 1/4. So now it tells us they're independent. So we can say by independence, the probability that A and B occur is the probability of A times the probability of B, which would be 1/4 times 1/4, which is 1/16. Or as a decimal to 4 decimal places, that would be approximately, or there is no approximate. For 1/16, there's no approximate. It is exactly 0.0625. That's why, by independence, we can state this. Okay, now for part C. What's the probability that for 2 independently chosen statistics teachers, the first will order 6 boxes and the second will order 2 boxes? Well, let's set up our events to ensure that this happens. So we're going to have to define our events similarly. I'm actually going to directly copy these here. No, there we go. Okay, yeah, that's lined up right. Backspace, backspace. Okay, so this, let's delete it. It's old info. Okay, so first one, the first orders 6, the second orders 2 boxes. Okay, now let's talk about our probabilities for these events. Now, for 6 boxes, we already know this probability is going to be 1/4. So the probability that B occurs is going to be 3/4. And how did I know this? This came from part A. Okay, again, now we're going to say by independence, we can multiply these together. By independence, probability that A and B happens. So probability of A times the probability of B that's going to be equal to 1/4 times 3/4, which is going to be 3/16. Or again, as a decimal, it's going to be 0.1875. Notice I said by independence, we can multiply them like that. If they weren't independent, we'd have to come up with a different solution. But they're independent. So we are Gucci as a gumdrop. Okay, D. What's the probability that for 2 independently chosen statistics teachers, exactly 1 will order 6 boxes? Okay, so what we need here is we want only one of them to get 6 boxes. So what we can do, since we want one to get 6 boxes, let's come in here and say, okay, here's what we're going to do. We're going to define events A and B as we did for part B. Meaning, teacher 1, event A is that teacher 1 orders 6 boxes. Event B is teacher 2 orders 6 boxes. Now, we only want one to actually get the 6 boxes. So let's come in here and say something to that regard. We only want one of the 2 teachers to order 6 boxes. That is, we want so what is it that we want? Well, let me make this in our commentary color here. Bold and blue. That is, we want A, let's say A gets 6 boxes. We want A and not B, or we want not A, but then B gets it. Now, notice these are 2 totally different events. We can't have one occurring while the other's occurring. One will occur or the other will occur. So let's note that these 2 events are mutually exclusive. Thus, So we either want that to occur or we want that to occur. So the probability that A and B complement or A complement and B occur is the probability that A and B complement occurs plus the probability that A complement and B occurs. Since they're mutually exclusive, we can add them and not worry about some intersection where they commingle, because they won't. One will happen or the other will happen. They will never come together. Okay, well, what is this? So by independence, so I'm going to put an equal here, but then I'm going to put a little note that says by independence. This is equal to the probability of A times the probability of B complement plus the probability of A complement times the probability of B. I am out of room down here, so let me make another line. Okay, so let's see here. Probability that A occurs. In part B, A occurs with a probability of 1/4 times the probability of not B. Well, B is 1/4, so not B has to be 3/4. Plus, then we do the probability of not A. Not A would be 3/4 times the probability of B is 1/4. That's going to equal 3/16 plus 3/16, which is 6/16. Now, if we reduce that, we get 3/8, which is, as a decimal, 0.375. There we go. So this one took a little bit more thought. This would probably be a good candidate for a free response AP question, where you have to actually think before you act. Don't just jump into it and go. Think about it. Think about it. Think about it. Okay, go now. Okay, so that's question 8. Now let's get to 9. So investigators recently reported the results in a study designed to assess whether or not the herb, St. John's wort, is effective in treating moderately severe cases of depression. The study involved 338 subjects randomly assigned to receive one of the 3 treatments: St. John's wort, Zoloft, or the placebo. The authors were primarily interested in whether St. John's wort performed better than the placebo and included Zoloft as a way to measure how sensitive the trial was to detecting antidepressant effects. The results are below. So this is another one of those contingency table problems. They're just going to ask you to find a bunch of probabilities, and they're probably going to make it a little complicated for you. So let's see. A says, what's the probability that a randomly selected subject had no response? Okay, well, let's see. No response over the total. So I'm gonna, when I name these, I'm gonna say F is full, P is partial, N is no. I'm gonna say SJ is St. John's. Then we've got the placebo. I'm gonna say it's PL. And then Zoloft is Z. Why did I say PL for placebo? Because I already used P for partial. Okay, so this is asking for the probability that we have no response. Well, it's going to be 192 over 338. Which is approximately, to 4 decimal places, equal to 0.5680. I mean, that's all we're doing. No response over total. That's it. This one was that simple. Let's see if B keeps it simple. What's the probability that a randomly selected subject was treated with Zoloft and had a full response? So Zoloft and full. That's what we're looking for. The probability of Zoloft and full. So Zoloft is 20, or let's see, Zoloft and full. That's going to be 27 out of our total. So 27 out of 338. Which to 4 decimal places is approximately 0.0799. So far, so good. We're just reading the table. Let's see about C. What's the probability that a randomly selected subject had a full or partial response given they were treated with St. John's? Okay, so they want the probability of a full or partial given St. John's. So this is going to be the probability. We're going to have to use conditional probability. So I probably should add that up here. By conditional probability, okay, so probability of full or partial and St. John's over probability of St. John's. Okay, now let's look at our table and see where that happens. So I need full in St. John's, I need partial in St. John's, and then I need the total for St. John's. So this is going to be 27 plus 16 over 113. Which 27 plus 16 gives us 43 over 113. which is approximately, to 4 decimal places, 0.3805. So full or partial in St. John's, and then over the probability of St. John's. That's because of the conditional probability. That's the whole given portion. Okay, D. What's the probability that a randomly selected subject didn't have a full response and was treated with a placebo? So probability that a randomly selected subject that didn't have a full response was treated with a placebo. This one is going to kind of be backwards. So what we're really wanting is the probability that we treated with the placebo given that they did not have a full response, meaning that they either had partial or no response. That's what we really want. So again, by conditional probability, okay, so this is going to be the probability of a placebo and partial or no response divided by the probability of partial or none. Okay, so let's see here. Placebo and partial or none. Let me get rid of this. Placebo and partial or none. So 33 out of 33 plus 66. Those are the ones that meet this one. Wait a minute. 33 or 13? My bad. 13 and 66. So 13 plus 66. Over the probability that they had partial or none. Partial or none. So 55 plus 192. Okay, well, 13 plus 66 would be 79. 55 plus 192 would be 248. Let me double check my math here. I did that in my head on the fly. Oh, 247. That's why I checked my math. Let me check the top now, because now I'm worried about the top. Nope, top is right. Okay, so then let's divide them to get 4 decimal places. Approximately 0.3198. Okay, so the probability that they didn't have a full response and they were treated by the placebo would be 0.3198. So this one was a little tricky. We had to kind of reverse engineer it some. Now, how did I get partial or none? Because this is F complement. Didn't have a full response. That's F complement. So that's how I got that value. Okay, that's number 9. Last one. Number 10. We're getting there. Okay, so they ask us to calculate. They give us all these probabilities. I'm not going to read it, but they give us these probabilities and say they calculate each of the following. And then say, show your work. In other words, again, don't just regurgitate some answer and say, oh, here it is. Blah, here it is. How'd you get that answer? How? Don't just tell me. Show me. Okay, so they say probability that they have at least one pet fish, that's what F means, given D, they have at least a dog. Well, this is the probability of a fish and a dog over the probability of a dog. Now, do we know fish and dog? Yes, it's 0.18. Do we know the probability of a dog? Yes, it's 0.32. Divide these and you get the 4 decimal places, 0.5625. Boom, you showed me. You didn't just do it. Okay, next one. The probability of a fish or a dog. Well, we're going to have to use the addition rule here. We're going to have to do the probability of fish plus the probability of dog minus the probability of a fish and a dog. Okay, so let's see. What's a probability of a fish? It's going to be 0.2. What's the probability of a dog? 0.32. And what's the probability of fish and dog? 0.18. So that's going to be 0.34. Okay. And the last one, I think. Yep, it's the last one. Probability of cat and dog. Well, there's different ways we're going to have to look at this. We can't just say, oh, cat and dog. We can't multiply them because they're not independent. But what do we know? What does this one mean up here? Let's take a second to think what this means. This probability of dog given cat is a probability that we have a dog and cat divided by the probability of a cat. What's this asking for? Probability of cat and dog. So what we can do is say, oh, wait a minute. Probability of cat and dog. That's the probability of a dog given a cat times the probability of a cat. Now we have the pieces to solve it, because this is going to be 0.30. Probability of a cat is 0.35. So times 0.35. It's going to be 0.105. So we had to use the info they gave us and then just kind of twist it around to work in our favor. That's the law of total probability. Hadn't used it yet, but it came up. So that's the review for chapter 6. Like I said at the beginning, it's a lot of math. Hopefully you're seeing that. A lot of math, very little words. But that's how this chapter is. So study it, know it, ask me questions if you need to, and good luck on your test.